Hello everyone, myself Bhagirip Kalal, Assistant Professor of LJ Institute of Engineering and Technology. Today I discussed Air Refrigeration System Part 2, Lecture number 4. Topic included in this lecture is actual Bell-Coleman cycle, which is different from ideal Bell-Coleman cycle. And topic 2 was to numerical based on Bell-Coleman cycle. Numerical based on Bell-Coleman cycle. Actual reverse Britten or Bell-Coleman cycle is different from ideal cycle due to non-isentropic compression, that is a 1 to 2 process, and non-isentropic expansion process, that is 3 to 4 process, and pressure drop in cold and heat exchanger, cold and hot heat exchanger, that is a 4 to 1 and 2 to 3, 4 to 1 and 2 to 3. Okay. Here I saw 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, and 4. It is an ideal Bell-Coleman cycle. 1, 2 days, 3, and 4 days because is actual Bell-Coleman cycle. Why it is occurs? Because of due to irreversibilities. Because of due to irreversibilities in compressor and turbine. That's why actual Bell-Coleman cycle is different. Due to these irreversibilities, the compressor work input increases. Compressor work input increases and turbine work output reduces. Actual work of compressor and turbine are given by work of compressor, work of compressor, work of compressor is equals to ideal work of compressor divided by efficiency of compressor divided by efficiency of, and work of turbine, actual work of turbine is equals to efficiency of turbine into ideal work output of turbine, ideal work output of turbine. So efficiency can be written as efficiency of compressor is equals to T2 minus T1 divided by T2 days minus T1, and we can remember as a small difference T2 minus T1 divided by large difference. That is a diagram. T1 T2 minus T1, the small difference compared to T2 days minus T1. That is a ratio of, you can find the efficiency of compressor by using of this ratio. Next, efficiency of turbine. T3 days minus T4 days, T3 minus T4 days divided by T3 minus T4. Again, small difference divided by large difference. Numerator value is less or denominator because efficiency value of efficiency is 1 and 0. So efficiency is between 0 to 1. So actual network output, the ideal work compressor minus ideal work of turbine. Actual work of compressor minus actual work of turbine. So we can calculate the actual net output work, net input work, net input work. Net input work is equals to actual work of compressor minus actual work of turbine. So now we do some numericals based on Bell-Coleman cycle. But before starting of numerical, we remember some important formula. Important formula Bell-Coleman. First, remember this TS diagram and PV diagram of Bell-Coleman. First formula is used, that is 1 to 2 processes isentropic compression. That T2 minus T1, T2 by T1 is equals to P2 divided by P1 raised to gamma minus 1 divided by gamma. If you know T1, if you know the temperature T1, then we calculate the T2. First, we calculate T2, and if we know the T3 temperature after after cooler T3 after cooler, then we calculate the temperature T4. Then we calculate T4. This formula is written as per the isentropic expansion process 3 to 4. So finally, first of all, we calculate T1, T2, T3, T4. Then calculate RE, refrigeration effect. RE, that is refrigeration effect. That is refrigeration effect. That is CP T1 minus T4. Here M is equals to 1. We take M is equals to 1. So per kg, answer comes in per kg, kilojoule per kg. Not 1 megapascal is equals to 10 bar. Remember, 1 megapascal is equals to 10 bar. Next formula, we find compressor work M Cp T2 minus T1, but we calculate in per kg, that's why M is equals to 1. Next, work done by expander. Expander taken as a turbine. So turbine work is equals to M Cp T3 minus T4. M is equals to 1. So answer kilojoule per kg. Net work is equals to compressor work minus turbine work. So net work is equals to compressor work minus turbine work. So final we calculate COP. COP is equals to refrigeration effect divided by net work and calculate COP. Alternative method for COP. COP is equals to 1 divided by RP raised to gamma minus 1 divided by gamma minus 1. What is RP? RP is equals to pressure ratio. P2 by P1 is equals to P3 by pressure ratio. P2 by P1 is equals to P3 by RP is equals to pressure. So it will start numerical number 1. So, numerical number in Bell Coleman refrigeration plant, the air is drawn from cold chamber at 1 bar and 15 degree, 1 bar at 15 degree and compressed to 6 bar. That means process 1 to 2. At 1 pressure equals to 1 bar, at 2 point pressure is 6 bar. That's why pressure ratio is 6. By P1 that is 6. RP value that is 6 and 15 degree is T1. Then air is cooled to 28 degree in the cooler. Air is cooled to 28 degree in the cooler before expanding in the expander to the cold chamber pressure of 1 bar the compression and expansion process are isentropic. Compression and expansion process are isentropic. Okay. Calculate COP of plant and refrigeration effect per kg of air, refrigeration effect per kg of air. So given data, P1 is equals to 1 bar, T1 equals to 15 degree, 88 Kelvin, because plus 273 to 88 Kelvin. P2 is equals to 6 bar, T3 is equals to 28 degree, which is equals to 301 Kelvin. Find out the COP and refrigeration effect. Find out the COP and refrigeration effect. First of all, before we calculate the answers for solution, we draw the TS diagram. So given T1, the value of T1 is equals to 15 degree. T2 we calculate by using of isentropic compression process, T1 T2 formula, and 2 to 3. T3 is also given after cooler. After cooler temperature is 28 degree. The air is cooled 28 degree in the cooler before expanding. This 3 is 28 degree. So we use the formula for isentropic compression process 1 to 2. P2 by T1 is equals to P2 by P1 raised to gamma minus 1 divided by gamma. So we know that T1 that is 28 degree. Okay. P2 is already we know that is a 6. P2 by P1 is special ratio 6 by 1 is to gamma. That is a gamma is understanding for air 1.4 for air that is a 1.4 minus 1 divided by 1.4. So finally T2 is equals to 480.53 Kelvin. 480.53 Kelvin. For isentropic expansion process, T to 4, T3 by T4, P2 by P1 raised to gamma minus 1 by gamma. So T4 is equals to T01 into 1 by 6 raised to 1.4 raised to there is a raised to 1.4 minus 1 divided by 1.4. So final T4 value is equals to 180.40. 180.40. Okay. So we know all the values of T1. T1 is equals to 15 degree, 288 Kelvin, and T2 calculated 480.53, and T3 already known, T01, T4 180.40. So refrigeration effect is equals to Cp T1 minus T4. Because we calculate per kg, that's why I am taken as a 1. Cp value for air 1.005, 288 minus 180.40. So finally we get Re, refrigeration effect, is equals to 108.13 kilojoule per kg of air. Per kg of air, refrigeration effect. Means that much of amount of heat absorbed by the refrigerator per kg of air, that is 108.13. Now, work supplied to the compressor. Work of compressor CP T2 minus T1. Again, put all the values 1.0005 into 280.53 minus 288. So, work of compressor is equals to 193.49 kilojoule per kg of compressor. So work done by the expander. So we get some work by the expander, that is work of turbine. We also say work of turbine or expander, WE or WT. The work of turbine is equals to Cp T3 minus T4. Everywhere a mass of air taken is 1 kg, because answers comes in terms of per kg of air. So work of turbine 121.203 kilojoule per kg of air. So W net, how we can calculate W net? Work of compressor minus work of turbine. Then 193.49 minus 121.23 is 72.8. Finally, COP. What is COP? COP is equals to RE divided by net work. Here W net 108.13 divided by 72.28 is equals to 1.49. 1.49. 1. So also we can calculate by alternative method. We derived one formula, lecture number 3, that is COP is equal to Coleman or theoretical or ideal COP 1 upon P2 divided by P1 raised to gamma minus 1 by gamma minus 1. P2, we know that value of P2 and P1 and gamma 6 divided by 1, 1.4 minus 1, 1.4 minus 1. So COP is 1.49. COP is equals to 1. Okay. Next problem number 2. Problem number 2. All the problems are different. Okay. Now next problem, a refrigerator working on Bell-Coleman cycle. A refrigerator working on Bell-Coleman cycle takes air into a compressor of at 1.81 bar and minus 5 degree. Minus 5 degree, that means 268 Kelvin. It is compressed in compressor to a 5 bar. So outlet of compressor pressure 5 bar. So that's why pressure is 5. And cooled it to 25 degrees centigrade at the same pressure, and cooled it to a 25 degree at the same pressure, that is 2 to 3. Same pressure, that is pressure is constant in 2 to 3 process, and 3 temperature 3 is given, that is a 25 degrees centigrade. It is further expanded in the expander or turbine to 1 bar and discharged to take cooling load. Isentropic efficiency of compressor. Here efficiency is given. Compressor efficiency is 85% and efficiency of expander, that is turbine, is 90%. Find the following values. Refrigeration capacity of the system if air circulated is 40 kg per minute. That means the mass of air circulation, mass flow rate of air is given, that is 40 kg per minute. And second, kilowatt capacity of motor required to run the compressor. That means power of compressor and COP of the system. The main things for this numerical is that here efficiency is given, isentropic efficiency and isentropic efficiency of compressor and turbine, which is 85% and 90% respectively. So in numerical, some things are little bit changed than previous numericals. What is it? Because efficiency is given, so we calculate the actual temperature of system. So we use this formula next. Given data is here. Isentropic process 1 to 2, T2 by T1 is equals to P2 by P1. So T2, we can calculate T2 424.46. But this T2 is the ideal temperature at outlet of compressor. But compressor efficiency is given, so we calculate the actual temperature of compressor. Efficiency is what? 0.85% is equals to T2 minus T1 divided by T2 dash minus T1. T1 is given, that is 268. T2 dash calculate, we want to calculate, and T2 is calculated 424.46. Put the all the value and we get T2 dash is equals to 452.07 kilo. Here also we draw a TS diagram for actual and ideal process. 1, 2 days, 3 and 4 days is the actual cycle, and 1, 2, 3, 4 is a ideal cycle. Okay. For isentropic process 3 to 4, for 3 to 4, calculate T4. T4 is equals to 188.15. That is the ideal temperature at outlet of expansion, of expansion or expander or turbine. But efficiency is given. That's why T4 dash is equals to 199. Efficiency is given, so we calculate actual outlet temperature of. So now calculate refrigerating capacity of the system. If you want to refrigeration capacity, it comes in terms of ton. So we required mass of air. So refrigeration capacity, but RE is different. RE refrigeration effect is per kg in terms of per kg. If we multiply mass with RE refrigeration effect, then it is called refrigeration capacity. So mass of air into Cp into T1 minus T4 is, we put the value mass of air 40 kg per minute, so minute converted into second. So answer is 45.91 kilowatt. 45.91 kilowatt. So refrigeration capacity convert into ton. That's why we divided by 3.5. So value is 13.12 ton. Now motor capacity to run the compressor, or net work of compressor. How can calculate net work? W compressor minus W expander, but we use the actual temperature differ from the ideal temperature. So in place of T2 we use T2 days, in place of T4 we use T4 days, and then calculate power of compressor, that is 56.8 kilowatt. 56.8 kilowatt. Here we use MA, mass of air, which is given in numerical. That's why we use mass of air and converted divided by 60 and converted into second. So power is 56.8 kilowatt. That is a total power required for run the plant. So COP of the system is equals to capacity divided by network. That is 45.91. That is a capacity in kilowatt divided by 56.8 in kilowatt. So COP is equals to 0.8. COP is equals to 0.8. So finally, we got value COP is equals to 0.8. COP is equals to. Next problem is an air refrigerator working on Bell-Coleman cycle. An air refrigerator working on Bell-Coleman cycle takes in air at 1 bar at temperature of 10 degree centigrade, the air is compressed to 5 bar. The same is cooled to 25 degrees centigrade in cooler before expanding in the expansion cylinder to cold cold chamber pressure of 1 bar. The compression and expansion laws followed are EV raised to 1.35 is equals to constant respectively. Determine COP of the plant and net refrigeration effect per kg of air. Takes CP is equals to 1.009 kilojoule per kg Kelvin, and R, that is gas constant, is equals to for air is equals to 0.287 kilojoule per kg for air. So given data is P1, P2, T1, T3 is given, and we'll draw TS diagram. So changes is that it is a non-isentropic process. Here in numerical non-isentropic process, because it followed PV raised to 1.35 is equals to constant for both compression and expansion. So we use this value 1.35 instead of 1.4 instead of 1.4. So polytropic process 1 to 2 and is replaced by gamma is replaced by n, T2 by T1, P2 by P1, N1 minus 1 divided by N1. So we calculate T2, that is 29.53 Kelvin. For polytropic process, T2 N2. Here, N2 is also changed, that is 1.3. So in place of gamma, we use 1.3. So T4 is equals to 205.55 Kelvin. So here I calculate all the temperature T1, T2, T3 and T4. Now we calculate refrigerating effect per kg of air. Refrigerating effect is equals to Cp T1 minus T4. Here M is equals to 1. So calculate refrigeration effect in terms of per kg. So Cp for air 1.009, temperature T1 283, T4 205.55. So answer refrigeration effect is 78.14 kilojoule per kg of air. Now compressor work done, that is WC. Before in ideal cycle for compressor we write as a MC T2 minus T1, but in place of Cp we write N1 divided by N1 minus 1 into R. So because value of gamma 1.4, but here it follows polytropic process. That's why for polytropic process compressor work is equals to N1 divided by N1 minus 1 R T2 minus T1. So put all the values and we calculate the compressor work 162.21 kilojoule per kg of air. And next expander work done. So it is also follow the polytropic process. For polytropic process, expander work is equals to N2 divided by N2 minus 1 R into T3 minus T4. All the values and calculate the expander work is equals to 114.97 kilojoule per kg of air. So net work is equals to W compressor minus W expander, that is the 47.23 kilojoule per kg of air. Now calculate the COP of the system. COP of the system calculated by refrigeration effect divided by net work. Here mass of refrigerant is taken as 1, mass of air or refrigerant taken as 1. That's why RE in terms of per kg and W net in terms of per kg. The value and we get COP of the system is equals to 1.65. So today I discussed 3 problems, 3 different types of problems, every time asked in the exams. So thank you so much.